All right, so we're going to pick up with displaying functions. And although there's really three typical ways it's done, the two big ones are equations, yeah, that deserves a capital, and graphs. Okay, equations are great for computation. They will give you exact outputs for exact inputs, whereas graphs are great for, I want to say intuition or getting a feeling for the thing. So for getting a feeling for the relationship. That's not spelled right at all, even remotely. Okay, let's try this again. Relationship. Okay, now the third way of displaying functions is with a table. And this is most common for just listing some data. It's really only useful for small amounts of data, small lists. Okay. And even though we do include some problems and some examples for it, typically humans were just so visual that graphs are fantastic. Whereas like tabular, when you glance at it, you'll see a bunch of numbers and it's easy to kind of gloss over. Equations, for those who have been doing math for a while, you start to get a real feel for it at that level as well. It's still a little bit harder, but they're fantastic for computation. So, for example, the degree Celsius is you take your degrees Fahrenheit and you subtract 32, and then you multiply that by 5/9. Okay, so if I were to graph that relationship, and I can call it a relationship, I can call it a function, it doesn't matter because functions are relationships, then degrees Fahrenheit is my input, whereas degrees Celsius is my output. And when Fahrenheit is at 32, Celsius is at 0, and then it's just kind of a line. But this line, you know, there's no reason that I can't go down into negative temperatures. So here we go. And you can just really quickly at a glance get a feel for how Fahrenheit and Celsius are related. They both go up together, and you can kind of see like, oh, well, wait a second, 0 degrees Fahrenheit is much colder than 0 degrees Celsius. So anyway, just stuff like that. At this level, maybe you can quickly glance at it and get that same feeling, and if so, it's probably just because this is really just a line. This is mx plus b, and my slope is 5/9 after I distribute, and my y-intercept is whatever 5/9 times 32 is. Okay, so let's look at something much more complicated to really, really drill home what I'm talking about. Let's consider population. So population as a function of time is some constant, e to the rt over 1 plus, and then there's a whole bunch of constants and parameters at play here. All right, so let's just run through what's going on. So K is a carrying capacity. All right, so how many of this species can be supported in this environment? Yeah, okay. Maybe we can only support 10 billion humans on Earth, in which case K would be 10 billion, right? Something like that. All right, C, you can kind of think of this as the initial population. That's not quite true, but it's related to initial population. So like if this was bacteria and I originally just had a very small amount of bacteria, like 2, then C would be something kind of close to 2. Whereas, so really what's going on, okay, let's just finish this out. So R is the growth rate. And T is just time. Maybe it's in years, maybe it's in minutes. If it was bacteria, it might be in minutes. So when you plug in 0, this is the first population measurement, which we often call the initial population. population. And if you plug in t equals 0, then the exponentials, right, e to the 0 is just 1. So what you get is c over 1 plus c over k. And this is the initial population that you measure. And you should imagine that k is something that's really big. Okay. And if k is really big, then c divided by k is really small. It's practically 0. It's kind of like 0. So this is why I was saying c is related to the initial population. C divided by 1 plus something that's basically 0, it's still basically c, right? C over 1 plus something that's very small is still kind of like c. Okay. But technically, this whole more complicated object is your initial population. Okay, so great. That is how to model population if you know carrying capacity and you know the growth rate and all these things. Not possibly too helpful. So now let's look at a graph of it. So here's time, and my y-axis is my population. Okay, and maybe right here is my carrying capacity k, right? So it could be 10 billion or something like that. And maybe right here is my starting population. Well, I'm going to have some exponential growth that mellows out, and then I kind of slope off, and I end up having this horizontal asymptote, my carrying capacity. I cannot have a larger population than is allowed, and the carrying capacity is the maximum allowed, so I kind of start to mellow out. And for different carrying capacities and different growth rates and different C's, like you can get a lot of kind of different looking curves, okay, or different, there'll be a similar lazy S shape, okay, but again, as we vary different parameters, the curves have similar shapes, but they just kind of change where exactly they're at. So, all right, at a glance, I can look at this curve and see that, okay, well, as time goes on, I'm going to approach k. That's much less clear here, right? Like, at a glance, can you look at that and say, as t gets really large, this becomes k? That's very hard to do, but it's very easy over here. So that's the type of thing that I mean. You get a feeling with a graph. However, if I were to say, hey, suppose time was measured in months, for example, okay? Then at 1 month, what's the population? That's very hard to do. I can't just read off this value. But here, I could plug in 1 for t, and I can get you an exact value. Again, I'm imagining I know what c is and I know what k is, right? So that's what I mean by equations are great for computation, graphs are great for getting a feeling for something. All right, let's talk about when a function is invertible. Previously I mentioned functions, they pass the vertical line test. I think I just made it as a remark when talking about the circle. With unit conversion, this always passes the vertical line test. And similarly with all of these examples, they all pass the vertical line test. Now, there's something even more special going on with unit conversion and with these examples here. They pass what's called the horizontal line test. So if I draw a horizontal line, it only intersects my graph at 1 point, or at most 1 point. And that's true here as well. And in fact, I tried to resemble that would be true with the unit conversions because I can have an input as miles and an output as kilometers. But similarly, I could have an input of kilometers and output of miles. And if I were to graph this relationship, 1 mile is equal to 1.6 kilometers. Technically, it's something like 1.61 and blah, 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 but we're not going to worry about that. And so if I have a distance in miles and I want to convert to kilometers, so my kilometers should be a function of my miles, then if I know my miles, I would multiply by 1.6. So this is equal to 1.6 times however many miles it is. So again, that's just a line. Its slope is 1.6. And again, it passes both the horizontal and the vertical line test. So, all right, to pass the vertical line test means you're a function. To pass the horizontal line test means you are invertible. So we have invertibility. Invertibility. Again, I'm terrible at spelling. So, all right. So a function is something where for each input you have exactly one output. Invertible is if for each output it comes from exactly one input. Okay? And so that's sort of what it means in words. Algebraically, what this means is you can solve for x as a function of y. So the way I'm going to write this down in shorthand is you're kind of given y as a function of x, and then what you can do is figure out x as a function of y. For example, let's just look at a line, y equals mx plus b. I can solve for x. I can say, well, x is equal to y minus b divided by m. So on the right-hand side, I have my input is y and my output is x, and on the left-hand side, I have my input is x and my output is y. This is invertible. Okay. I also, something we're going to see a lot in this course, I could have something like y is equal to the natural log of x. But I could solve for x. X is equal to e to the y. So again, this is invertible. And again, x is a function of y when I was given y as a function of x. I can just solve for it. Okay, so when can you not do this? So kind of the easiest and most classic example is to say y is equal to x squared. If you try and solve for x, you might be tempted to say x is equal to the square root of y, but it's not quite true. There's a very key thing missing, which is plus or minus the square root of y. So if I were to graph this relationship, it's not a function, but it is a valid relationship, then square root of y would look like this. That would be the positive root y. But there's also negative root y, which looks like that. And you can see it fails the vertical line test, so it's not a function. But similarly, back when I was just given the square root, x squared, it fails the horizontal line test. So it's not invertible. For example, if this was y equals 1, so my output is 1, there are two different inputs. There's positive 1 and there's negative 1, and both of those inputs produce the output 1. So for each output, it comes from exactly one input. That's not true. In this case, there exists an input. For example, y equals 1. Not an input, an output. Oh gosh, clean it up. Here we go. No. There we go. Output. For example, y equals 1. That comes from two different inputs. Okay? So it fails to satisfy the definition. It's not invertible. And I kind of gave away, I was making a list here. There's algebraically what it means to be invertible. There's graphically. This would be the horizontal line test. And it's if a horizontal line intersects your graph at most one point. And indeed, let's look at natural log. Looks like this. No matter where I draw a horizontal line, it'll intersect my graph at most one point. All right, so that is invertibility. And invertibility is fantastic because essentially when you have two variables, variable 1 and variable 2, you can just go between them flawlessly, no ambiguity. And this is exactly what happens with things like unit conversions. Oh, and I also want to remark, earlier I said it's less common to go between seconds and hours. I think that's less common in daily life. It's actually super common in a physics classroom because you might need to convert from meters per second to miles per hour. And so you're going to have to deal with the meters versus the miles and the seconds versus the hours. And that's just a whole nasty beast. Okay, so invertibility means the output comes from exactly one input. It equivalently means it passes the horizontal line test. It equivalently means you can solve for x as a function of y. What does it mean in the tabular form? So I've been avoiding talking about functions as tables, but let's just, if I had some hypothetical little table listed out, so here's my input column and here's my output column, people might be tempted to write this as x and y, and that's fine, you can do that. I just kind of hate it. I really prefer to think of it as input and output because I really want us to think of inputs as being these like physical objects that we're measuring because we're scientists, and outputs as being other physical objects that we care about. So I don't want to get lost in the whole what's x and what's y. I really want to give meaning to these things. And after that whole rant, I'm just going to put down numbers as an example. So if I have an input of 2, 3, 4, that kind of thing, and an output of 17, 4, -10, and 20. Okay, so previously I talked about what graphs are great for. They're getting a feel. What equations are great for? It's for doing exact computation. When are tables even useful at all? Why do we ever even bother talking about them? And the answer is maybe you cannot put a table into an equation. Maybe you're not so fortunate as to be able to do this, right? I mean, look at these numbers. Do you see any obvious pattern? Do you see a way to do it? Probably not. And you could graph these points, and they'll kind of just show up as dots. And maybe that's a better way to do it. Maybe not. But at a glance now, I can ask myself, is this a function? To be a function, every input has to have exactly one output. And in this case, since all the inputs are different, then yeah, it's already done. So what would a not function table look like? So I could have an input and an output. And essentially what would have to happen is some input would have to be repeated. So since I'm lazy, I'm just going to repeat 1. Okay, and maybe the first time the output I get is 17, and the second time the output I get is 12. And then maybe these other two things are the same as my first example, so 3 and 4, they give me -10 and 20. Okay, so this is not a function because one input gave me 2 different outputs. One time it gave me 17, and one time it gave me 12. Not a function. Okay, what would it mean to not be invertible in the tabular form? Well, this time I need one output to possibly give me 2 different inputs. So we can build that. So here's my input, here's my output. And so for example, maybe I want to get the number 17 in 2 different ways. Maybe it's going to be associated with both 1 and 2. And now I can just start filling stuff in. It doesn't matter. Okay, this is a function. Yep, but it's not invertible because there's an output that's associated with 2 different inputs. This is a function, and it's invertible. Okay. All right. What else is on the agenda? Combining functions. All right. Combining functions. Okay, so look, you can add and subtract functions, you can multiply and divide functions, and truthfully, you've probably done this without even thinking about it. So I could take, for example, x plus 7, and I can think of this as one function, f of x equals x plus 7, or I could think of it as the addition of 2 functions. Maybe g of x is x, and h of x is 7. So f of x is g of x plus h of x. So you've really been adding functions all along. It's just a matter of whether you think of a single expression as the addition of 2 things or as just one object on its own. And being able to think of one object in multiple ways is very useful in mathematics, if not in life. Even using these 2 functions here, I could talk about g of x times h of x, which is just a really fancy way to say 7 times x, right? Because here's 7 and here's x, and I'm multiplying them. I could talk about h of x divided by g of x, and this is a fancy way of talking about 7 divided by x. And once division starts to creep in, then I have to worry about, well, wait a second, what if I'm dividing by 0? That's never allowed. Okay. So we can combine functions, and sometimes things are going to pop up where we might need to worry about if the combination is valid. And if it's not valid, typically it's only going to be for certain special cases, and so we say, okay, just don't allow that to happen, but otherwise it makes sense. So we can add functions, we can subtract functions, we can multiply, we can divide. When we do division, we might have to take out certain x values or inputs that would cause the denominator to be 0. And that gets into domains. Okay. So the domain, here I'll make it singular, of a function is the set or collection of all possible inputs. Okay? So, if I have a function where the input is Kelvin, so it's a temperature function, and the output is degrees Celsius, then my domain, what's the lowest Kelvin? I want to say it's like 273.15. I'd have to look it up. I think negative 273.15 Kelvin is as low as you can go. There's nothing below that in terms of temperature, but I don't know of a cap to temperature. Maybe you can just keep getting hotter and hotter. So this is all possible temperatures I can plug in. These are all the possible inputs. I could be down at this negative 273.15 Kelvin, or I could just keep on going up and up and hotter and hotter and hotter. And then my range, this is all possible outputs. And I believe it's, in this case, it's the same because, wait, no, what is, I'm just so rusty on Kelvin, I don't even know. I believe that, oh man, you caught me. This is what happens when I try and make it up on the fly. All right, exercise. Let's do a math example. So what's wonderful about some invertible functions, so let's look at e to the x, for example. So here the domain is all real numbers, which I can write with this fancy r. I could write it as saying minus infinity to infinity, or I could write in words, I could say all real numbers. But no matter what you use as an input x, it's totally well defined. You can compute e to the x. Okay, the range, however, this quantity, e to the x, is always positive. So I'm never actually going to touch 0. I'm always going to be positive. And little fun fact, when you invert a function, you're just flipping x and y, which means you flip the domain and range. So the domain of the natural log, which is the inverse of e to the x, well, you can only input positive numbers. If you try and enter something like natural log 0 on your calculator, it'll say error. Okay, it's not defined. And its range, well, again, I'm just flipping these. It's all real numbers. Okay. So no matter what number you want to hit, you think of your favorite number, whatever it is, call it y. You can find an x such that y is equal to natural log of x. That's not true if I claim y is equal to e to the x. For example, you can never solve negative 1 is equal to e to the x. It doesn't happen. Okay. So in other words, the range of e to the x is smaller than the range of natural log. Okay. Okay, so how do you determine a domain? Well, you got to know some algebra and you got to know some life stuff. So uh, in this case, it's the context. Okay, I remembered from high school chemistry that Kelvin only goes so far negative, and I think this is as far as it goes, but I didn't look it up ahead of time. But you could also have to determine domain using mathematics. So, for example, square root, you can only put in non-negative numbers into a square root, right? Square root of -1 is not defined, at least not in the real numbers, although I would love to talk about complex. So in this case, the domain is, you could plug in 0, you can go up to infinity. So that would be the domain of the root x function. Okay, how about 1 over x? Here the domain is everything except 0. So you could write that in words. Never be afraid to just use a complete sentence in a math course. That's totally fine. You could write that in symbols by saying, hey, I can plug in any negative number I want, or, and this is what the union operator is, or this little u that I wrote, you can read it as the word or, I can plug in any positive number I want. But I just can't plug in 0. I'm just going to leave it like that instead of showing you all the different ways you can denote it. Another common function will be log, and like we talked about earlier, the domain of log is the positive real numbers. So for the most part, these are the 3 functions with limited domain that we're going to interact with. You can start to build more complicated objects by looking at function composition. So this is the last big topic. Let me just double check my notes really quick. Yes, okay. So function composition. Beforehand, let's do one quick example of combining functions in a way that, okay, so this might seem like a contrived word problem, but really combining functions is very common. So, okay, Jane sells pies. And maybe she sells them for $10 a piece. So then the revenue that she brings in, which is just the total amount of money that she's gained in sales, the revenue, it's a function of the number of pies that she sells. So N is the number of pies sold. Okay. And if she sells them for $10 a piece, then her revenue might be 10 times N. And her profit, which, okay, so the difference between revenue and profit is what you've actually earned, like it's your net gain basically, whereas revenue is your total earnings. So your profit, so we'll call this P as a function of N, and maybe she actually only makes $7 per pie because maybe she spends $3 in making them, and maybe she has some kind of operating cost that's independent of the amount of pies that she sells, and I'll just say it's $5 a day to like keep the electricity on and use some water or something. I'm just totally ignoring rent, but whatever. So now if I wanted to figure out, okay, what's her expenses? So her expenses as a function of how many pies she sells. So E as a function of N. Well, her expenses are just going to be her revenue minus her profit. That difference, that gap, is the money she has to spend to keep her business going. Okay, so what does that mean? So here's the math symbols, but Rn, or R as a function of N, is just 10 times N. So 10 times N minus, and then profit as a function times N is 7N minus 5. Okay, so I end up getting 3N plus 5. This is her expenses as a function of N. So we combine functions all the time because certain functions might tell certain pieces of information. We need to combine those pieces of information to find out new stuff. That happens all the time, even though I just gave you this kind of not so great example. Okay, function composition. Composition. So first, just symbolically, aka mathematically. Mathematically. All right. So part of why I like to think of functions as being you give me an input and I give you an output or something like that is because of function composition. So if you give me an input, there's some function f, and what f is going to do, it's going to take your input, it's going to multiply it by 17, and then it's going to add 2. Okay. Now, the way we write this down algebraically is I might say f of x is equal to 17x plus 2. But I really like to think of it as, what does it do to my input? It multiplies my input by 17, and then it adds 2. Okay, so that's the function f. And then maybe I have this function g, where if you give me an input, what g is going to do is it's going to take my input and it's going to square it, and it's going to subtract input. So symbolically, I might write g of x is equal to x squared minus x. Okay, function composition uses the output of one function as the input for another. Okay? So symbolically, I can talk about f of g of x, which this is just notation. The most common is to do one function inside of what's called the argument of the other, but it's this here. The other notation is circle notation, which is this little open circle, and it just means you compute g of x first, and then you feed that output into f of x. Here you compute g of x first, and then you feed that output into f of x. So, okay, what is my input for f in this case? And the answer is it's g of x. What does f do to an input? Well, it takes 17 and it multiplies it by that input, and then it adds 2. Okay, so in this case that's 17 times, and now g of x, here's g of x, so x squared minus x, and I want to put that in parentheses because that 17 is going to have to distribute, and I don't want to make an error, plus 2. Okay, so this function here is f of g of x. I took the output for g, and I used it as the input for f. All right, now let's look at g of f of x. All right, so what does g do? It takes the input, which in this case is f of x, it squares it, and it subtracts the original input again. So in this case, that's 17x plus 2 squared minus 17x plus 2, which again, I want parentheses because I have to distribute this negative if I were to keep going. So symbolically, this is what's going on with function composition. Let's look at computing something. So, for example, if I have f of g of, I guess 0 would be a kind of nice one. No, that might actually cause a little bit of, let's do 1. F of g of 1. Okay. So I'm going to work from the inside out. I first need to find out the output of g when the input is 1. So I need to compute g of 1, which is 1 squared minus 1, which is 0. So 0 is my output, and that is the input to f. This equals that. And now I just have to compute f of 0, which is 17 times 0 plus 2, so it's 2. Okay, so f of g of 1 is equal to, oh, where do you go? I lost my pen. There we go. 2. If I flip the order and I look at g of f of 1, let's see, so f of 1 is equal to, oops. So this step here is g of, and my input is f of 1, so I have to figure that out first. F of 1 is 17 times 1 plus 2, which is just 19. So 19 goes here. And g of 19 is going to be 19 squared plus 19, or sorry, minus 19. Okay. So notice these are two very different functions. In one case, I got 2, and in the other case, I got 19 squared minus 19, which is, much larger. And in any case, I used the output of one function as the input for another. All right, in this case, I use the output of g as the input of f, and here I use the output of f as the input of g. Okay, so what else is on the agenda? All right. As much as I would like to talk about where this is used in life, which it's used all the time, and like unit conversions, I guess really quickly, no, never mind. Instead, I'm going to defer you to Khan Academy. I will put a link in the description, Khan Academy, on where to go. But what's the little phrase? Modeling practice. Well, all right, I'll find the link. Oh, model with composite functions. So model with composite functions. All right, they have practice exercises and videos of sort of exercises showing how this can be used in life. And in later videos, I will try to think of some better uses for the sciences and things that we might care about. Anyway, that is all for now.